Hey everyone! Today we're diving into the foundations of engineering. Just like a building needs a strong base to stand tall, every project, whether it's a game, a robot, or an idea, needs solid fundamentals. In this video, I'll walk you through the core building blocks that will help you build smarter, faster, and more reliably. Ready to lay your engineering foundations? Stick around and I'll show you how. Coordinate systems are one of the most essential tools in engineering and a powerful key to unlocking cleaner, simpler logic in game development. In this video, we're going to break down how they work, why they matter, and why choosing the right one, Cartesian or polar, can make all the difference when implementing motion or behavior in games and simulations. I'll show you how just a bit of the right knowledge can let you create circular and linear motion in Unity with only a couple of lines of code. Let's jump in. Let's start with the basics. What even are coordinates? A coordinate system is a way of describing where something is in space. In 2D space, we say a point has 2 degrees of freedom, which means we need 2 values to specify exactly where it is. The most common system is the Cartesian coordinate system. That's where every point is described using horizontal, x, and vertical, y, distances from an origin. So if I say a point is at coordinate 4 and 6, that just means that it's 4 units to the right and 6 units up from the origin. Pretty intuitive. Here's a way to visualize this. Imagine we fix the x to a certain value, say x equals to 8. That collapses our entire 2D plane into a vertical line. The only degree of freedom left is the y direction. Then, if we also fix the y, say y equals 6, that vertical line collapses again. This time it collapses into a single point, and now we know exactly where we are. In other words, the point starts free to move anywhere in 2D space. The first condition, x equals 8, limits that freedom to one-dimensional line. The second, y equals 6, limits it even further to a zero-dimensional point. That's why we need 2 coordinates to fully describe a position in 2 dimensions. Just a quick note, in 3 dimensions we have, as you can guess, 3 degrees of freedom. We also have more complex coordinate systems, like cylindrical coordinate system and a spherical coordinate system, but we use them way less often because of how complex they are. Of course, Cartesian coordinates aren't the only game in town. Another way to describe a point's location is by using polar coordinates. Instead of x and y, we describe the point using 2 different values. The first is its distance from the origin, we call it the radius, and the second is the angle it makes with the x-axis, we call it theta. So that same point we saw before at 8 and 6 in Cartesian coordinates can also be described in polar coordinates by having a radius of 10 and a theta angle of about 37 degrees. Same location, just a different way of thinking about it. Unity, much like this graph, uses Cartesian coordinates. That's why this graph is divided into squares with x and y axes. But if we want circular motion, trying to directly update the x and y every frame can get pretty messy. Believe me, I've been there. It does work, but I think for this particular case, there's a simpler, more intuitive way. Instead of updating both x and y with complex expressions, we can use polar coordinates and just update theta over time, then convert the result to Cartesian right before using it. And that conversion I talked about earlier? It's super simple. If a point is on a circle with radius r at angle theta, then its x value in Cartesian coordinates is equal to the r times the cosine of theta. In a very similar way, the y is equal r times the sine of theta. This can be derived pretty simply by using a bit of trigonometry. Anyway, with this we can describe circular motion with circular tools rather than linear or straight line tools, which makes more sense, right? Now let's apply it in Unity. We'll start fresh in Unity. Drop in a floor sprite and a circle sprite and create a new C# script for motion. Inside Visual Studio, We defined an enum for the motion types: stationary, circular, horizontal, and vertical. Next, we set up our key variables. We'll set up the cycle time, the radius, which sets how wide the motion is, theta, this is our polar angle, which we'll be updating, and the motion center, which is the origin of the movement. We'll just use the object starting point for this video. Now for the core logic, the move object method. For stationary, we just return, no movement. For circle, we update theta using this equation. Theta equals 2 pi times the... Well, hold down there, cowboy! What the fuck? Let me just explain what happened there with the pies and everything. Cause it ain't so simple. What? Somebody get this dude out of here? Anyway, as many of us know, angles can be measured in degrees, where a 90-degree angle is a quarter of a circle, 180 degrees is half a circle, and 360 is a full circle. In engineering, we often measure degrees in radians, where 2 pi radians is full circle. That is because the perimeter of a circle is 2 times pi r. So pi is half a circle and half pi is quarter of a circle. That's just another way to measure degrees, but it has the advantage of working out better with our equations. Unity and most math libraries use radians by default, so because of this, and for educational purposes, we're going to use radians in this project. So what we did in our code was to set our angle to 2 pi, which is a full circle, times how many cycles have passed by now. So let's say that our cycle is 4 seconds long, and it's been 2 seconds, which is half a cycle. Then this will result in an angle of pi radians, which is half a circle. After we updated our theta, all we need to do is update the object's actual position. We'll do it by setting it equal to the motion center plus the object's location in Cartesian coordinates, which if you remember, we convert from polar by using x equals r cosine of theta and y equals r sine of theta. And that easy we have circular motion. Of course we need to remember to call this function from the update, but we all remember that, right? We don't forget to attach our script to our sprite. We pick our parameters, and voila! We have stationary motion. Alright, I'll change it. And there it is. We have an object moving in a circle. Next, we want to implement horizontal and vertical motions. To explain how this is gonna work, let's move back to the graph for a quick demonstration. As you've already seen, we can create a circular motion by using x equals r times the cosine of theta and y equals r times the sine of theta. We then increase the value of theta and we get our circular motion. This happens because the sine and cosine functions make the x and y values oscillate in such a way that creates a circle. But what would happen if we keep the y constant and allow the x to oscillate? Then we will get a horizontal motion. The same thing can be said for the y. If we hold the x constant and we allow y to oscillate, we will get a vertical motion. Back in Visual Studio again, all we have to do to implement the horizontal and vertical motions is super simple. We just copy the circular motion code and put zeros in the appropriate x and y values. So we'll put a 0 on the y for horizontal motion and a 0 on the x for vertical motion. Alright, that's it for this one. We now have circular, horizontal, and vertical motions. And you didn't even have to wrestle with complex Unity code. Play around with the parameters, see how they affect the motion, and maybe even try combining motions if you're feeling spicy. This foundation is super powerful, and we'll build on it in future videos. If you found this helpful or learned anything new, go ahead and hit that like button. It really helps the channel grow and reach more people. And if you want more videos like this about mechanics, Unity, or just cool engineering essentials, subscribe and stick around, because I've got a lot more ideas that I can't wait to share with you guys. Thanks for watching, and I'll see you in the next one. Cheers, guys!